on these two models.
Share with us your screen and
yes. So can you see my screen?
yes, excellent. You can start whenever you are ready.
Is it full screen?
Now
Yes.
it's full screen.
Okay, thank you very much. First of all, I would like to thank the organizers for giving me this opportunity to have this talk. I'm going to talk about distribution amplitudes of light diquark. This work is done in collaboration with Daniel and some other collaborators. So we are studying diquarks. The notion of diquark is a phenomenological idea which was introduced by Biermann in 1964, and then Ida and Kobayashi in 1966, and Lattenberg and Tassi in 1967. At that time, they considered baryon as a composite state of constituent quark, and diquark. The diquark is correlated quark-quark pairs. So baryon can be considered as a bound state of 2 particles rather than 3 particles. So the quark-diquark model is conceptually more complicated than 3-quark model. However, it is computationally simpler. So because there are only 2 degrees of freedom, so people can use this quark-diquark model to calculate the baryon mass. If we start looking, we will find that there is phenomenological evidence for diquarks everywhere. As I said before, the diquark was born in the regularities of baryon spectroscopy. And the diquark may also play a role in the exotic states, as Gernot mentioned yesterday. We might have diquark correlations in compact tetraquarks and compact pentaquarks. An additional approach to pin down the diquark correlations is to look at the nucleon to resonance transition form factors, as Jorge mentioned yesterday. And we can also study the space-like nucleon form factors to look at the how QCT supports the diquark correlations. In the following, I will take example. Take this nucleon form factor in the limit of large Bilken X limit as an example to showing that how QCT supports diquarks. So we are looking at the neutron and proton form factor structure functions F2 in Feynman's pattern model. F2 in neutron and F2 in proton can be written in terms of the up quark and down quark distribution function in proton multiplied by some charge squares. So if we take the ratio of F2 in neutron divided by F2 in proton, we will have this expression. Here we have neglected the relatively small contribution from strange quark or even heavier quarks. If we consider this ratio at large X region, so we can expect the C quark contribution to be small. This is reasonable because C quarks are dominate at a low X region. So if we consider large X region, the valence quarks are dominate. So this ratio F2 in neutron divided by F2 in proton can be further simplified to have only two quantities, the up quark distribution function in proton and the down quark distribution in proton. So naively, if we think the up quark distribution is equal to twice the down quark distribution, which means the spin flavor SU6 symmetry, this ratio is equal to 2/3 when x goes to 1. However, as you can see in the right figure, the experiment data at large X region are apparently smaller than the 2/3 limit. What if the ratio goes to 1/4? This can be explained by a diquark case, which means the one up quark in the proton carries most of the proton's momentum, so it can be viewed as a fast parton, and the other valence up quark and down quark are combined to as a low momentum scalar diquark. So only the fast up quark contribute to this ratio at when x goes to 1. So this ratio is equal to 1/4. So this is an example showing that the scalar diquark can exist in the proton. As mentioned by Jianwei, that the ratio d divided by u at x goes to 1 is still with large uncertainty, but nevertheless, the this ratio d divided by u is smaller than 1, so the up quark is the fast parton and scalar diquark can exist. A recent extraction of this ratio from a nuclear DIS extraction indicate that this ratio will become a constant when x is larger than 0.6, and when x goes to 1, this ratio will be equal to 0.47, which is in agreement with the prediction from perturbation QCD and Dyson-Schwinger equation approach. As you can see, the extraction is this blue band. And more recently, this ratio is determined by the marathon collaboration. So the blue dotted blue dots are the marathon result. I take this paragraph from the marathon collaboration paper, saying that the highest x points are consistent with the ratio turning to a value between 0.4 and 0.5 at x is equal to 1. And this is inconsistent with the prediction from perturbation QCD and quark content rows, for which this ratio is 3/7 at x is equal to 1, and with a recent prediction that trace strong interaction with using the Dyson-Schwinger equations, where the diquark correlations is in nucleon are the consequences of dynamical carrier symmetry breaking, for which this ratio at x equal to 1 become between 0.4 and 0.5. So in the framework of Dyson-Schwinger equation, we have not only a scalar diquark, but also around 25% to 35% axial-vector diquark contributions to proton. So another instructive actively considering a proton as a Borrmean bound state, as mentioned by Jorge. So proton can be considered as a system constituted from 3 bodies, no 2 of which can combine to produce an independent asymptotic 2-body bound state. So you have diquark clusters, and the diquark can dynamically break up and reform. And the diquark clustering is an emergent phenomenon which is driven by the emergence of hadron mass. And diquarks are color and confined, even though this is not true if the rainbow ladder truncation is used in the associated scattering problem. So you have to have corrections to the rainbow ladder truncation in diquarks. And diquarks are soft. They have electric magnetic size. Their charge radius is larger than the Meson counterparts. So this leads me to my next point. Since diquark is not a point-like particle and have charge radius, so we can study the quark distribution, the diquark. So if we want to describe the hadron's measurable properties in terms of the probability typical quantum mechanics, we can use the light from wave function, as Kipney mentioned. And in this talk, I'm focusing on distribution amplitudes, which is proportional to the integral of the light from wave function with respect to the transverse momentum K curve. And the distribution amplitudes features in formula describing hard exclusive process. So we are studying this matrix element. In this matrix element, the Wilson line vanish in the light cone gauge, and we assume that it is not quantitatively important in the computation of two-particle distribution amplitudes. We are considering leading twist distribution amplitudes. There are 4 twisted 2 operators. So another thing is worth mentioning that it had been pointed out in this article that the quark distribution in proton can be written in this convolution expression, which means the quark distribution in proton can be equal to the quark distribution in the capital Q, they call it a parent, and then convolute the parent distribution in proton. So if this capital Q is the diquark, so this distribution is the quark distribution in the diquark. So once we know the quark distribution in the diquark, we might have access to the quark distribution in a proton with this convolution expression. So this is the background of this study. Now I'm moving to the method we are using, which is the Dyson-Schwinger equation. So we need the quark gap equation and diquark beta sorpita equation. In the quark, we use the bottom-up approach, which means in the quark gap equation, we will model the gluon propagator, and we will use the rainbow approximation for the quark gluon vortex. In the diquark beta sorpita equation, we will use the we will use the ladder approximation for the quark antiquark scattering kernel. If we look at the diquark beta sorpita equation carefully, we will find that the color factor in the color factor is equal to minus 2/3 for the diquark, because diquark is the color anti-triplet invariant. And however, in the Meson beta sorpita equation, the color factor is 4/3. So the difference between the color factor for the color factor between diquark and Meson is minus 1/2. So if we redefining the diquark beta sorpita amplitudes and making use of the charge transformation gamma matrix, we will find that the diquark beta sorpita kernel is smaller than the Meson kernel by a factor of 2. So in one way, you could say the effective interaction in diquark is reduced by a factor of 2 compared to the interaction in Meson. Alternatively, if we solve the Meson beta sorpita equation with eigenvalue lambda is equal to 2, then the corresponding diquark state will have eigenvalue is equal to 1. So if we look at the Diquark total wave function, it must be anti-symmetric. The color wave function is anti-symmetric because Diquark is in color anti-triplet. If we consider the ground state, there is no orbital momentum, so spatial wave function is symmetric. So this leads to the combination between the flavor and spin wave function is symmetric. So if spin is 0, then isospin is also 0. This is a scalar Diquark. If spin is 1, then isospin is also 1. So it's axial vector Diquark. So we will focus on these two cases in the following. And if we look at the parity of the Diquark, it's equal to the intrinsic parity of the quark times the parity from the angular momentum. So the Diquark overall parity is opposite 1. And since the quark and antiquark have opposite intrinsic parity, so for meson, the overall parity for meson is negative 1. So the ground state Diquark always have positive parity, and ground state meson always have negative parity. If spin is 0, then the ground state Diquark is scalar Diquark, and the ground state meson is still the scalar meson. If spin is 1, it is axial vector Diquark and vector meson. So there is a one-to-one correspondence between a scalar Diquark and a pseudo-scalar meson. So the scalar Diquark beta-sorped amplitudes have exactly the same Dirac basis as pseudo-scalar meson beta-sorped amplitudes, and the same for axial vector Diquark and the vector meson. So we studied Diquark distribution amplitudes. As I said, there is one-to-one correspondence between scalar Diquark and pseudo-scalar meson. And in the framework of Dyson-Schwinger equation, there are plenty of studies on pseudo-scalar meson distribution amplitudes. So the extension to a scalar Diquark distribution amplitudes is very straightforward. We use this expression. Here chi is the beta-sorped wave function, and we use this light front projection delta function to project the covariant beta-sorped wave function onto the light front to get the Diquark distribution amplitude, scalar Diquark. And the same thing for axial vector Diquark, we extend the vector meson distribution amplitudes to the axial vector Diquark distribution amplitudes. Here in axial vector Diquark, there are two distribution amplitudes, the longitudinal one and transverse one. Here, in the transverse one, we use this operator to ensure the leading twist operator is sigma plus perp. Additionally, the decay constants that appears in these three expressions are purely theoretical objects and do not correspond to any physical decay constants of Diquarks. So before going to the Diquark distribution amplitudes with realistic interaction, it is worth to look at the Diquark distribution with a contact interaction. Then we will have some general idea that what we can expect in the realistic interaction. So with contact interaction, in the quark gap equation, there is a Coulomb propagator. If the Coulomb propagator is a constant, then this is called contact interaction. As a consequence, the mass function in the quark propagator is momentum independent. So this looks like the Nambu-Jono-Lozano model. And with contact interaction, the beta-sorped amplitudes for pion and the Diquark can be written in the following forms. Since the Coulomb propagator is at constant, the interaction is constant. So consequently, the beta-sorped amplitudes is also independent of the relative momentum. After solving the beta-Sorbit equation, we get the mass. First, we get the mass. In current limit, we get the pion mass is equal to 0, and scalar diquark mass is equal to 0.77. So we see a large difference in the mass between the pion and UD scalar diquark. Pion, because pion is a number Gaussian mode, but diquark is not. And then we get the beta-Sorbit amplitudes for pion and scalar diquark. We say they are quantitatively similar, have with the same sign and ordering.
Excuse me, 5 minutes left.
Yes, thank you. I'm almost there. So the beta-Sorbit amplitudes, we find the diquark amplitudes is roughly 30% smaller. And then with the mass and beta-Sorbit amplitudes, we can calculate the distribution amplitudes. We find the pion distribution amplitudes is a constant. As you can see, it's the green dashed curve in this figure. And the diquark, we get the diquark distribution amplitudes first two non-trivial moments, and these two moments can be reconstructed with this function. The result is this yellow curve in this figure. As you can see, the scalar diquark distribution amplitudes is appreciably narrower than the pion distribution amplitudes. So the contact interaction produce constant distribution amplitudes for pion, and this result is also obtained in the Nambu-Jono Laceno model. So with contact interaction, the pion is a point-like particle, which suggests that with contact interaction, the valence quark or antiquark in pion can carry any value of the light from fraction of pion's total momentum with equal probability. And however, the contact interaction produce the scalar diquark distribution amplitudes, which is not a constant. So a diquark is not a point-like particle with contact interaction. And we can say the valence quark in the diquark is less likely to carry a large light from fraction of the system's total momentum than that in the meson. The main reason is that in the scalar diquark, the mass of the scalar diquark is much larger than the pion mass. So consequently, the scalar diquark distribution amplitudes is narrower than the pion. So then we comes to the realistic interaction. We use the gluon propagator, which is, we use the massive decoupling type of gluon propagator, which is finite and non-zero in the infrared. We use this function to model the gluon propagator in the infrared. As Kipney mentioned, we calculate the distribution amplitudes at this hadronic scale. So we only have, at this hadronic scale, we only have dressed quark. We don't have C quark or gluon distribution. We use this process-independent running coupling to determine this hadronic scale. And the distribution amplitudes is reconstructed from the Maillard moments. First, we get the diquark mass and decay constant. So here we consider four states: scalar diquark, pion, axial-vector diquark, and rho. Here is their masses and decay constants. For the time reason, I will skip this. And then we get the scalar diquark distribution amplitudes. So here there is a asymptotic distribution, which is 6 times x times 1 minus x. This table, you can see the moments for the distribution amplitudes, pion, scalar, diquark, and asymptotic distribution. You can find, if we focus on the second moment, you can see the scalar diquark second moment is smaller than the asymptotic. However, the pion second moment is larger than the asymptotic second moment, which will indicate that the scalar diquark will be narrower and the pion is broader than the asymptotic distribution. And the result is given in this right figure. As you can see, the yellow solid curve is scalar diquark, and the green dashed is pion. So the scalar diquark is narrower and taller, and pion is broader and flatter than the asymptotic. And then this computation can be repeated for the axial-vector diquark. Here I also listed the moments. The main feature is that the axial-vector diquark second moment is smaller. However, row moments is larger than the asymptotic limits. Additionally, the longitudinal moment is smaller than the transverse moment. So in this figure, from the top to the bottom is the longitudinal polarization, axial-vector diquark distribution, and then transverse polarization of the axial-vector diquark, and then asymptotic, and then row meson. So other than the narrow behavior, we find the transverse polarization is broader than the longitudinal polarization. So this brings me to my summary. We studied the distribution amplitudes of light, scalar diquark and axial-vector diquark using beta-Sorbita equation with ladder approximation. The main feature is that we find the diquark distribution amplitudes is narrower than their meson counterparts, which indicate that the valence quarks sequestered with the diquark collision inside the proton is less likely to participate in the hard interaction than the bystander valence quark. For the outlook, I'm interested in the nucleon distribution amplitudes and GPDs and TMDs. So this concludes my talk. Thank you very much.
Okay, thank you very much, Minghui, for your nice talk. Questions for Minghui? I actually have one. I always thought that the distribution amplitude, in the case of the contact interaction framework, it will be constant with respect x for any meson because we are ignoring relative momentum. Looks like it is not the case for a scalar diquark, and it is mostly related with the mass, or the difference between the mass of the pion and the scalar diquark. So it's just the mass that is producing the difference with respect to constant. I don't know, imagine that I compute the row meson in the contact interaction framework. What I'm gonna get, a distribution amplitude which is a constant, or something similar to the case of the scalar diquark, for example?
Yes, so I'm not very familiar with the contact interaction, but yes, I think in the contact interaction, so the pion is distribution amplitude is constant, and the scalar diquark is not a constant. It is narrower. The main reason, yes, I think is that the mass of the diquark is much larger than the pion. Yes, as you know, the only difference from the diquark and the meson is that the interaction in the beta-Sorbita kernel is is equal to half of the meson's beta-Sorbita kernel. I'm not sure, but it seems that this 1/2 factor can brings a lot of effect in in the distribution amplitudes, not only the mass, and then the distribution amplitude is much narrower. I'm not sure I answer your question.
I think that we can discuss later if you want, Minghui. It is quite fine. Thank you very much. Any other question or? Yes, you can go ahead.
Yeah. Do you see any changes in the size or mass in hadron when you take into account diquark? Thank you.
I think I have slides showing that the mass in the diquark is always larger than the mass, and the charge radius of the diquark is larger than the meson. Yes, which comes from the electromagnetic form factors of the meson and the diquark.
We should move on in any case. Thank you very much